So in this video, let's talk about how to determine the amount of resonance structures. Essentially, how do we draw resonance structures? All right, so let's start off with a simple example. Let's say on an exam you're given O3 and we ask how many resonance structures or how many resonance structures there are of this molecule. Now, the point of this video, as you should be in organic chemistry now, the point of this video is not really to illustrate the point of how to draw Lewis structures. At this point, you should be familiar with that, right? So I could give you in this instance, I'm going to give you the Lewis structures, but we're going to ask how you're going to rearrange those bonds, right? And that's a critical point. So for the O3 molecule, I essentially have something like this, right? And you should be very comfortable with drawing Lewis structures. The point of this video is actually not to draw Lewis structures, but the molecular formula looks like this. So the idea is that how many Lewis structures I could actually draw for O2, right? It's not a reaction, so you want to make sure your arrows go in both directions. Now the idea is that the only thing, let's define what a resonance structure is. A resonance structure is pretty much we're just moving our electrons. We're getting the same molecule. It's just a different representation of the molecule with respect to where the electrons are. My charges or my overall charge should not change, right? Only electron rearrangement. Now, the best thing you want to do, or the best way to attack Lewis structures, is to always start from the electron-rich areas. And in organic chemistry, those are usually in the form of negative charges. So where you see negative charges is potentially where you want to start moving your electrons from. All right, so those are electron-rich area. Now, I see here that I have 3 pairs of lone pairs, a negative charge. All right, I could actually take a pair of lone pair, form a double bond here, but at the same time, this is nonsense, right? I can't have 1, 2, 3, 4. This will make the fourth bond now, and two pairs of and a pair of lone pair around oxygen. So that will force me to move one of the bond in the form of lone pairs on the other oxygen. All right. So in essence, if I redraw my structure, right, now I have an additional lone pair on this oxygen. I still have these two. I have not changed anything about them. And now I have a single bond, right, because I moved this. Now over here, notice where my electron arrow is going, I'll form a double bond now. So this becomes a double bond. And now I only have 2 pairs of lone pair, right? My lone pair on the middle oxygen is still here, right? We haven't done anything to it. Now notice, if you do your formal charge count, and the point of this video is not to do formal charges, right? You should be very comfortable with that now. But the idea is that my oxygen on this side now becomes a negative charge, and this stays a positive, right? I haven't touched the middle oxygen. All right. And a quick way to know how we do our formal charge is essentially you look at the atom of interest. So let's say this, for example, is oxygen. So we go from the periodic table. We say oxygen has 6 valence electrons, and we subtract that from the amount of electrons pertaining to oxygen, right? So this oxygen actually has 1, 2, 3, 4, 5. So this is 6 minus 5, and this is plus 1. All right. So this is a shortcut way of calculating the valence electrons. Right? If you're confused about how we calculate a formal charge, again, I've made several videos about how you can calculate formal charge, again, using a shortcut, right? So again, to illustrate the point again real quick, you might be saying, well, the total electron around oxygen here is 2, 4, 6, 8. No, that's not what we're saying with respect to the formula. We're saying how much is actually pertaining to the oxygen, right? So this becomes 1, 2, 3, 4, 5, right? Remember, these are if you take a look at this bond, this is a single bond, and we have 1 electron coming from this oxygen and 1 coming from this oxygen, but we only care about the electrons coming from the middle oxygen, right? So that's how we get the 5. So pause this video and ask yourself, are there any more resonance structures that we could draw off this molecule? And the idea is no, right? Now, a very important thing to point out here is that the overall charge of my molecule is still 0 on both sides. Right? Nothing changed, right? The only thing that changed was me moving the charges, which represents me moving electrons. All right, let's do a more complicated one. and I'm gonna give you the molecular formula. So, well, I'm gonna give you the structure. So let's say both are structured in molecular formula. So let's say we're given CH3CNO, right? And we have something that looks like this, right? Right, so this structure is given in the problem. How many resonance structures can we draw for this compound? How many resonance structures can we draw? Well, we sure can draw a lot, but let's see how much, right? So the idea is, where would you start with moving electrons? Start from the electron-rich areas, right? So there's no negative charges here in this formula, so we can't go by that logic. But we see lone pairs, and lone pairs are a good source of electrons, right? Lone pairs are great sources of electrons. So I'm going to start with nitrogen because it's electron rich, right? So I could actually form a triple bond here. I'm going to move this lone pair in the form of a triple bond here. But at the same time, carbon cannot have 5 bonds now, right? So I have to alleviate that 5 bonding by taking a single bond and putting it on the oxygen in the form of lone pairs. So this will give me something that looks like this. Now my nitrogen has a triple bond. It's lost, right? The lone pair is gone. It has a triple bonded to a carbon that now has a single bond, right? Because we've taken 2 of these electrons in the form of lone pairs to put on the oxygen, right? So now we have these 2 lone pairs that did not change, and the arrow is pointing that we now have a lone pair on the oxygen, right? Now notice that this molecule is neutral. So in that sense, this molecule should also be neutral, right? If we get something else, that means that we're changing the compound, and that's not what resonance structures are about. Now, if you do the formal charge real quick, you will see that nitrogen has a positive 1 charge and oxygen has a negative 1 charge. So the overall charge on the molecule is neutral, right? If you do the formal charges real quick, nitrogen will give you 5 minus 4, that's plus 1. Oxygen will give you 6 minus 7, which is negative 1, right? Now, the idea is, can we draw any more resonance structures for this compound? Do you think? Is there a possible way of drawing any more resonance structure for this compound? And the idea is, yes, we can still draw resonance structures for this compound, right? So I could take this lone pair and form a double bond between the carbon and the oxygen. At this same moment, I have to move these electrons in a pair of lone pairs to the oxygen, right? Because carbon cannot have 5 bonds, right? Now, that's all well and good. And essentially, we've ended up at the same place that we started, right? Now, nitrogen is going to get its lone pair back, right? And it's going to be double bonded to carbon, and this is going to be double bonded to oxygen. So we've started up with where we initially started. But if you notice, I can also form another bond between the carbon and oxygen, give that a triple bond, and move another pair of a single bond with respect to with respect to the triple bond in the form of lone pairs on the nitrogen. So this will actually give me, here's my CH3. I have a single bond in nitrogen, but now I have 2 pairs of lone pair on my nitrogen atom. Right? This becomes a single bond because we've removed the double bond essentially. Right? I have a carbon now that's now triple bonded to an oxygen. Now these two lone pairs are gone, right? So I only have this lone pair on my oxygen. Now, is this a plausible structure? Of course, right? Let's do our formal charges, right? Nitrogen, we have 5 electrons from nitrogen, and we have 1, 2, 3, 4, 5, 6. So this is 5 minus 6, right? So nitrogen is going to get a -1 charge, right? So the nitrogen is actually negative, right? What about the oxygen? The oxygen we get from the periodic table, that's 6 valence electrons minus 1, 2, 3, 4, 5. So this is 6 minus 5, and that's actually a +1 charge. So this oxygen is actually a +1 charge. All right, and this is pretty much all we could get. These are the 3 lowest structures of this molecule. Now, like I said before, if you're not comfortable with formal charges, I've made several videos with respect to uh, the formal charges for with respect to calculating formal charges, right? But the main point is you should see that we're just moving the electrons around with no alternation of the compound. So it's still the same structure, we're just moving the electrons around. Again, or notice our overall charge again is 0 here, it's 0 here, and it's 0 like we started. Let's go to one more. Let's say on an exam you're given this molecule. Let's say on an exam you're given this molecule. How would you draw? How many resonance structures can we get? How would you draw? Where would you think about moving the electrons first? Right? How would you do it? Well, the first thing I'm going to do is I see where the electron rich area is. I see a negative charge. That means I have electrons. This is an electron rich area. So that means I can move electrons starting from that area. Now I have 2 places to go, right? I could go here, this direction, or I could go this direction, right? This direction really wouldn't make sense because essentially uh, I wouldn't have any more electrons to move if I put a double bond here, right? So this direction does not make sense. But I could put a double bond in this direction and move the electrons elsewhere, right? So that's the first thing I'm going to do. I'm going to take these lone pairs, form a double bond here, right? But if I form a double bond there, carbon will now have 5 bonds, right? Impossible. We do not want that, right? So I could take this double bond and actually form a double bond here. If I take this double bond and form a double bond here, right? Then again, the carbon is having 5 bonds, right? So I could take this one of this single bond in the obviously in the double bond and form a lone pair on the oxygen. So essentially, when I arrange my when I get my structure again, this is what I have. I now have the double bond in this section, right? I also have a double bond in this section, right, where my arrow is pointing, right? And essentially, I have a single bond to my oxygen. But now, remember, in organic chemistry, I specifically did not give you the lone pairs, but please remember, there's essentially 2 lone pairs on this oxygen, right? So now I've added an extra one. And let's hope this works. All right, so now I've added an extra one. Right? So what are the formal charge? Well, this oxygen immediately becomes negative. Right? If you do the formal charge again, which is not what we're here for, but you could do the calculations yourself. This oxygen becomes negative. Notice that the overall charge is still negative. Now pause this video and ask yourself: is there another? Do you think there's another structure that we could get for this molecule? And the answer is actually yes, right? And let me use a different color, right? So if I actually take this, I could actually take this electron or take one of these electrons, reform a double bond, and actually kick this double bond onto the carbon that's right here. right? So if I look at this, essentially what I get, I still have my double bond here. Now I have a double bonded oxygen, only 2 lone pairs, but now I have a lone pair on this carbon, right? And if we do a formal charge, you'll see that this carbon is actually negative. So these will actually be the 3 resonance structures that, whoa, right? So these will actually be the 3 resonance structures that we would get for this molecule. Now, if you can't see this, think about this being a carbon in the middle, right? So let me just, right? So if you can't see this, think about this being a carbon in the middle, right? So if I have a carbon that has a bond, which is what I'm representing right here, it also has another bond that's being represented right here, and it also has another bond that's being represented right here. Right now, I have a lone pair on the carbon. Now, if we do a formal charge, you will see that carbon from the periodic table actually has 4 valence electrons, right? And then if we take the total number of electrons pertaining to the carbon, which is 1, 2, 3, 4, 5, this is 4 minus 5, and that's actually -1, right? Notice again, the overall charge of the molecule does not change. This is -1, this is -1, and this last compound is -1. The only thing we're doing is rearranging electrons. I hope this helps.